pick up where we left off yesterday. If we have two rational or two polynomials and we're dividing them, that gives us a rational function. When we want, there's multiple things that we have to determine for a rational function, and one of them is a horizontal asymptote. And we talked the horizontal asymptote. Its main purpose is to tell us what happens kind of on the ends of the x-axis. And when x gets very large in the positive direction and very large in the negative direction. And a kind of elementary style way of deciding or determining that is just to evaluate, okay? Just to pick very large x values and plug it through your rational function and see what you get. And you can do that with very large negative numbers and see what you get. And do that consecutively, bigger and bigger x values in the positive and negative direction. And you'll see that your y values tend to approach the same value. And what happens, though, is that we can go through some algebra and basically determine, which we did, determine that the leading coefficient or leading term is that dominating feature that is going to tell you ultimately what y value you're going to evaluate at when x gets really, really big. Does that make sense? And there are three different scenarios that could happen. The first scenario is when we have like 3x squared over 3, or let's go to x cubed, okay? And that is scenario A here. And I completely forget because I always, and it's different from textbook to textbook. If you read different textbooks, sometimes they use N and M, sometimes you use A and B, whatever they want to use for these. Sometimes you see C and D. I always forget which one's which. N is at top. Is that N for numerator? I don't know. Maybe that's the way you can remember it. But I always forget, and ultimately, if I forget which one's N and which one's M, I'm going to get that option and this option confused. I'm going to transpose them, okay? So I don't really remember this. What I remember is that I've got three options. Leading terms can have different exponents in that orientation where the top is smaller. We can have an orientation where they are the same, and we can have an orientation of where the top is bigger and the bottom is smaller in regards to their degrees. Okay. I know that, and hopefully you do as well, that the leading term is going to be that determining factor, okay, for in behavior. So if I compare them and totally disregard what this blue box says and what my asymptotes are, just do the division over here. What's going to happen with these x squareds and these x to the third when I do the division? It's going to leave me with a 1x on the bottom, right? And then all I have to do is think, okay, well, what happens? Because this is essentially, remember, this is y equals, because this was my rational function, but I'm only worried about the first two terms. The idea is now y equals that. So what happens to this y value as x gets really, really, really big? As I do that, as x goes to infinity, what is y going to? It's going to be 3 over an infinity, so it's going to approach a 0. Okay? Does that make sense? That this denominator is going to get huge, and a very small number divided by a very huge number gets close to 0, right? Does that make sense? So knowing that I can compare my leading terms, I can cancel variable components if they're different exponents, and then do the substitution with x being really big and see what I get. And that takes place of having to memorize A, B, and C over here.
What did you say you realized that?
We'll talk about that here in a little bit. The next one, okay, again, this is y equals, okay? What happens to the variable components here? Cancel out completely. So I get y equals 3/2. And now if I substitute an x that is very, very big, substitute in here 100 billion. Well, what's the y value going to be? 3/2. Okay? So that's the situation that we started with yesterday that said if your exponents are the same, then you just compare your leading coefficients through division, and that's your horizontal asymptote. Okay? This one here is, I'll put a line here, it's a rare occasion, okay? And there's gonna be maybe a day that we kind of totally devote to this kind of asymptote. But now if I look at these, where is the x going to remain when I cancel? Yeah, so I'm gonna get y equals 3x over 2. So now as x, let's say x is equal to 10, y would be 15, right? If x is equal to 100, y would be 150, correct? As x goes to maybe 1,000, y would be 1,500. Does that make sense? If x is 1,000,000, then y would be 1.5 million, right? That makes sense? Okay. Now, as x, these x's are getting bigger and bigger, right? X is going to infinity. What is y going to? Y is also going to infinity. Okay? Therefore, there is no horizontal asymptote. Okay? What you actually end up getting is what we call a slant asymptote. And that slant asymptote, it basically is an asymptote that is either a line or another curve. That line has a slope to it other than 0. Does that make sense? Okay, so if I were to graph, let's just see if we graph that one. Like y equals 3 x to the third divided by x squared. Yeah, that's kind of dumb. Because it obviously gives me a line that does follow that asymptote, but doesn't. Let's go plus x. See if that changes the thing. Okay. So here, we don't have a horizontal asymptote. Okay? We still have an asymptote, a vertical asymptote at 0. Can't divide by 0, right? So these curves will never touch the y-axis. Okay? But can you kind of see that this portion of the curve right here and this portion of the curve are following some other type of structure? If I look at, and let me put a 2 down here like we had in the other example. It's not going to change much. Do that. If I type in y equals 3 halves x, does it look like the actual curve is following that line? Okay, so that red line right there, if I get out here, is the curve approaching that? Get all the way out here, zoom in, you can still see it, they're separate. So what's going on there is that red line is actually then referred to as a slant asymptote. Okay. Now, there are things that we could do that would look like, let's see this, 4th degree here. Okay. So now we don't have a slant asymptote. Okay. What we end up with is, if I do the division here, don't we get something like 3x squared over 2? We get that blue curve right there. Do you see how the gray one is actually kind of following that blue curve? Okay. So that blue curve, it's an asymptote. Okay. We call that an oblique asymptote. Okay. Now, we don't spend a whole lot of time talking about those. We do spend, like I said, almost a day talking about slant asymptotes again. But slant asymptotes get kind of wrapped up into oblique asymptotes. Well, basically what we argue is if you have 2 categories, you have slant asymptotes, or sorry, you have horizontal asymptotes and you have oblique asymptotes. But if your oblique asymptote is a line, we call it slant. Does that make sense? Okay. You guys have seen the word oblique before in geometry. Do you guys remember taking like cylinders and then, or pyramids, and then slanting them? So if I had like a, let's see here. Oblique cylinder. No. Geometry. This has been 2 years ago. Oh, yeah, so it would have been, yeah. So this would be an oblique cylinder. It's not, like a pop can is a right cylinder, right? This would be an oblique. Okay. So we've seen that, and it's that idea of being kind of slanted or to the side or something like that. Okay. So that being said, so that, like I said, that category, that's why I kind of put this line here, that category, we're not going to see a whole lot of those right away. Okay. We're going to work mostly on A and B, and once we get that kind of figured out and understood, then we'll make the transition to talking about this third type of asymptote. Okay. When we go through the process of graphing a rational function, there's going to be like 6 or 7 steps to this. 6 or 7 things that we want to find out. Okay? We already have all the algebra skills to do them. We just need to remember how to do them. Okay? The first thing that we're going to do, the first 2 things, are going to be finding vertical and horizontal asymptotes. Okay? So I want to go through this problem here, and I want you guys just to take a minute and see if you can factor the top and the bottom of this, because that's the first thing that you do every single time that you ever come across a rational function. You need 2 versions of that rational function. You need the expanded version, and you need the factored version. Okay, so go ahead and take that on your own time here real quick and factor. All right, did we get those factored forms up there? 3x plus 1 times x minus 1 on the top, x minus 2, 2x minus 1 on the bottom. Now, that procedure right there is why we've spent so much time so far this year trying to factor. Okay? You can kind of maybe see that there's going to be situations where we might end up with like a cubic or a quartic or a quintic up top, and then a cubic or a quartic or a quintic on the bottom, and we have to use a rational root there. We're going to have to use all of our factoring techniques. Yes? Where? This is x plus 2? Yes, you're right, because that plus sign right there. Yep, you're good. Thank you. So those are what we get, right? So when we're determining asymptotes, okay, this version over here is going to tell me vertical asymptotes. This version right here, okay, so the expanded version is this one, and this is the factored. The expanded version tells me horizontal asymptotes. What's your horizontal asymptote if I look at this expanded version? Yeah, you're going to look at those 2 things, right? You're looking at leading terms. And because the exponents are the same, x squared and x squared are going to cancel out. And when x becomes really big, you get y to be 3 halves, right? Okay. If I look at this one, okay, the factored form, what am I not allowed to divide by? Not allowed to divide by 0. So what number would give me 0 there? -2. And what number would give me 0 there? -1/2. And yeah, you're right, +1/2. So if I do that, those are equations of my vertical asymptotes. Does that make sense?
I didn't know.
All right, so what I want to do now, so that is all I wanted to do on this problem, is make sure we understand the places or the locations of how to find horizontal asymptote and vertical asymptotes in all rational functions. It's the same every single time. Does that make sense? Okay? What that does for us if we go into a graphing scenario, okay, whether we're doing this by hand, on paper, Desmos, GeoGebra, whatever, doesn't matter. The first thing that we do when we graph our rational functions now are to put in those asymptotes. So we said y asymptote, or so horizontal asymptote is 3/2. And then we had x equals positive 1/2 and x equals -2, right? Those are our asymptotes. And those then, my hope is that you see that that breaks our graph into 6 separate regions, right? Okay. Now, what happens, and we're going to have the ability to find some of these points very easily, but basically what we're going to try to do is determine, okay, if I have a value of like -3, okay, as my x value, and I take my function, so I'm going to take my function 3x squared minus 2x minus 1 divided by 2x squared plus 3x minus 2. All right, so right now, okay, I'm not going to ask it to graph because I don't want you guys to see this yet. But right now, the idea is I don't know where my graph should basically be existing right now. Okay, should my graph be maybe existing in that region there? Okay, or should it be existing in that region there? Does that kind of make sense? Okay, and the only way that I can determine that is if I take a value of like -3 and run it through my function. So if I take g of -3, and it gives me that number right there, right? Okay, so 32/7, that's almost 4, right? Okay, so does it make sense that when I have -3, I should have a point kind of up there somewhere? Yeah. Okay. That means to me, so my dotted lines are kind of like a cage, where my point cannot get outside that cage now, or my graph cannot get outside it. So as we move our points, what?
Oh my God.
I already did that.
Oh my, dude. Anthony, dude. Trying to learn. Trying to learn, Anthony. Sometimes I think they don't happen.
All right, so I can't draw on this, but yeah. So the idea then is as I take this point and it becomes essentially a new point, I've got 2 options. So I'll just trace this and see if this works. My point, my A point can either go this direction, okay, or it could go this direction. But if it goes this direction, what's it going to have to do? So it's going to have to do something like that? Okay, so if it does something like that, think about this. So it would have gotten sucked close to that asymptote and then turned back. What does that violate? Vertical line test. So that's not a function anymore, right? So it can either, that point can either go up or it can go down, but if it goes down, what do I cross? Okay, so I cross the horizontal asymptote when I go down, right? Which is not out of the question. It could happen, okay? We could cross horizontal asymptotes. There are some graphs that would look maybe kind of like that. That will occur. But we will have done the algebra that tells us that happens already before we start graphing. Does that make sense? So right now, I'm going to tell you, we're not crossing that horizontal asymptote. So the only thing that point can do is move kind of like that. Does that make sense? Okay. Now, if I graph, I'm going to say if x is less than -2, let's graph g of x. Is that exactly what g of x does in that region? Okay, and if my graph is existing in that region, because it has to be a function, there's no way that it can exist down here at the same time. Does that make sense? Because then it would fail the vertical line test. Okay, now I'm going to come over here and I'm going to ask, what does g of maybe 2 look like? Well, g of 2 would be 7/12. So if I graph 2 comma 7/12, gives me that point right there, correct? Does that point then have the same behavior, but as I move it to the right, it's going to get sucked up to the asymptote? And as I move it to the left, I can't go up, but I'm going to have to go down, right? Can't go up because of that asymptote. And we right now, I'm going to tell you that we've done the algebra already, and we know that we're not going to cross that asymptote from 1/2 to the right, okay? So then if I ask this thing, if x is greater than 1/2, graph g of x. So that's exactly what we would have anticipated to happen, right? Now, the one place that kind of stinks is what happens in the middle here, okay? Well, it could be. It could be a parabola-ish, but it could be cubic-ish as well, okay? Because we've already done the algebra. If we would have done the algebra already to determine whether it crossed the horizontal asymptote or not, we would have, okay? So if I graph that stuff in the middle, you do actually cross the horizontal asymptote in the middle, okay? To get that stuff in the middle, what we would actually have to already done, and we're going to do this in the next example, is that we would have identified an x-intercept, we would have identified a y-intercept, and we would have done the algebra to see if we cross the horizontal asymptote. And if I have those 3 points, that gives me a pretty good structure for graphing that region in the middle. Does that make sense? Okay. What you did say, like you could have. There are some graphs that this is going to get kind of messy when I draw this. Wish I had my other tool that worked, but you can have graphs that do have kind of a oh, I want that one. You said a parabola in the middle. So you might have ones that kind of do that, and then you'll have, it won't be always like parabolic. It might be, let's see, you should put another point in here. Like something like that in the middle, okay? It just depends on what the two polynomials, numerator and denominator, look like in your rational function and how they relate. All right, so what I want to do is come down here. I'm gonna put these up, but I'm not going to sit here and let you guys write all that stuff down. If you want to write that down, go back to the video, go to the notes that are printed out, or on Schoology or whatever. And these are guidelines. They're not set in stone. I don't always do them in this order. Step 1 and step 5, I always do first and last. But the things in the middle, they can kind of float around. They're independent. Okay. First thing you always have to do is factor. 100% of the time, always have to factor. Okay, so that's the first step. Then what you're going to go through is you're going to try to find asymptotes. Okay. Vertical and horizontal. That's what I always do first. Vertical and horizontal asymptotes. When we talk about vertical asymptotes, there's a special situation where you might have like a common factor, like x plus 2 at the top of the rational function, and x plus 2 at the bottom. When you have that, that is a special situation where you don't necessarily have an asymptote. You have what we call a hole. So we'll look at those kind of at the same time that we look at vertical asymptotes. Okay. Then we'll look at horizontal asymptotes. Okay. The next thing we'll do is we'll determine x-intercepts, y-intercepts, if we haven't done that already. And then the next part will be, do we cross the horizontal asymptote? We'll have a question that says, cross horizontal asymptote, yes or no. And we'll run through the algebra that tells you that. Okay? Once we collect all that information, then we'll take that information and we'll drop it on the graph. And hopefully that gives us everything we need to graph. If it doesn't give us enough, then we'll do test points. Like we did in Algebra 1, where I choose an x value, evaluate, get the y value back, and plot that point. And hopefully then a few of those will then create a comprehensive graph for us. Okay? The one thing about these is that there's a lot of components. I'm not saying individually the components themselves are not that hard. Okay? But if we're doing 7 different things on one problem, there's places where you can go awry. There's places where you might get kind of trained. Just the examples that maybe we see that 9 out of 10 of them don't have a hole in them. Okay, maybe 9 out of 10 of them don't cross a horizontal asymptote, and then the 10th one maybe has both those things, and you forget to do that on the 10th one, right? So if we can keep every single problem structured the same, we should maybe mitigate the most we can those issues of forgetting to do something on one of these, okay? So what I like to do is make just kind of a list of things that I need, okay? I'm going to need horizontal asymptotes. I'm going to need vertical asymptotes, okay? At that time, I'm going to ask, are there any holes? Okay? And the reason I'm going to do that is because those two things kind of work in tandem. Okay? For instance, let's look at this real quick. Just give you an idea of what a hole would look like. If I have a function that is like x plus 2, x minus 3 in factored form over, let's do another one, x plus maybe 4, and then divide that then by x plus 2 times x plus 5, x plus 1. If I graph it that way, you would anticipate having an asymptote at -2, at -5, and at -1, right? Mm-hmm. Do we have one at -2? If I look at x equals -2, is there an asymptote there? No. Okay? And the reason there's not an asymptote there is because when there's a common factor in the top and the bottom, there's actually a hole there. Now, GeoGebra and really any graphing calculator that you see will not put a hole here. But right there where my cursor is should be an open dot. And I can guarantee that that's going to happen if I say f of -2. What does it give me? It says it's undefined, right? So it means there is no point there. So holes override asymptotes. Does that make sense? And it's because of that cancellation technique. Basically what happens is if I graph that function and then graph this function, so I cancel out, because the argument is x plus 2 and x plus 2, those should cancel each other out, correct? So if I cancel them and graph that, okay, is that the same thing? Oh, stupid. Control V, let's name this G. All right, so would you guys agree that the blue and the green functions are the same thing? They're 99.999999999% the same. What's the difference? The hole, okay? The blue or the green one has a hole at that point. So the point would be -2 comma A. That point right there, okay, does not exist on the green function. That should be an open dot right there. So it should look your graph would look like that instead. Okay. But when we're doing this using like a GeoGebra or Desmos, it doesn't fill that hole in automatically for us. ourselves. We have to do that ourselves. So that's where holes and vertical asymptotes, that's why we do them together here, because they're related somehow, okay? Occasionally. Or they interact with each other occasionally. The next thing we're going to do is find x-intercepts. We're going to find y-intercepts. We're going to ask, do we cross the horizontal asymptote? And some people like to ask that question right there. I don't. And I think in this example, you're going to see why I asked this question at the end. We'll go through the algebra, but sometimes you determine whether you cross the horizontal asymptote or not through the other information. Okay? And we'll talk about that at the end. And then we will graph. Okay, so this next part, I'm going to put an asterisk on it. We might need other test points. And that's a maybe. I don't know if we'll need them. It just depends on where our x-intercepts, y-intercepts, and all those other components kind of lay on our graph. Okay? First thing you have to do in order to generate any of this stuff is you have to completely factor these two things. So when we completely factor these two things, the bottom is an easy one. Was x plus 2, x minus 1. The top one, so it's going to be, what, negative 8, negative 1, and 8. So it's going to go 2x squared plus 8x minus 1x minus 4. So take a 2x out. Gives me x plus 4. Take out negative 1, x plus 4. So we should have 2x minus 1 and x plus 4, right? Okay. The one thing about this stuff, guys, is as we move through, the idea is that we should be getting more and more proficient with our factoring. So sometimes we'll just kind of run through that factoring real quick because we need to get that so we can address the other concepts. So because there are no common factors here, no common factors, right? On top and on bottom. So that would tell us that this question about holes is not applicable. They don't exist in this one. Okay? Now, this version here tells me my vertical asymptotes. This version here easily tells me my horizontal asymptotes, or asymptote. So if I want my horizontal asymptote, we look at the expanded version and we look at the leading terms, right? So what's that tell me my horizontal asymptote is? Y equals 2. Okay. In the factored version, vertical asymptotes are where you would divide by 0, right? So this stuff here is telling me where I would divide by 0. What are the x values that would produce division by 0? X is negative 2, and x is positive 1. Okay? Now, your asymptotes, remember, they're lines, so they need to be equations. Okay? So x equals not just negative 2, not just 1, but x equals negative 2, x equals 1. Same thing with my horizontal asymptote. Okay? X-intercepts. Okay? X-intercepts, going back to algebra 1, what is the y coordinate for every x-intercept? 0. So what we basically do is we take this factored version, set it equal to 0. Because an x-intercept is where y is equal to 0, right? Okay. What would you do if I had that green equator, that green expression equal to 0? How would you solve that equation? What would you do first? Okay, so you're going to multiply by this denominator, right? If I multiply by that denominator, is it going to go away on the left-hand side? Okay, so I'm going to multiply both sides by x plus 2 times x minus 1. That's going to cancel on the left-hand side. And what do I get when I multiply that by 0? Get 0, right? What did we just really do? We set the what equal to 0? Set the numerator equals 0. Every single time you do one of these problems, and you're asked for the x-intercepts, you're essentially saying, okay, my rational function equals 0. And then solve for x. Well, the first step would be multiplied by the denominator. The denominator is always going to be multiplied by 0. So it's just going to leave you always the numerator set equal to 0, right? If you were to look through a textbook and it walks you through this process, the instructions in the textbook will just say your x-intercepts are where the numerator is equal to 0. They never explain why. That's the why. Okay? So, where are my x-intercepts? What's this one going to give me? Yeah, x is 1/2 and y is 0. So my hope is that you see that once it's factored, a lot of the work is already done. We just got to pull the information out of that factored version then. This one's going to give me x of -4 and a y of 0, right? Okay. Y-intercept. Y-intercepts are pretty easy to find as well. But we use the expanded version to do it. What is your x-coordinate for the y-intercept? 0. So if x is 0, doesn't that go to 0? Doesn't that go to 0? 0, 0, what are you left with? -4 divided by -2 gives me 2. So x is 0, y is 2. Okay. Now, here's why I like to do horizontal, cross the horizontal asymptote last. Is because the information is already telling me that I do cross it. You have a horizontal asymptote of y equals 2, right? Did we just find a y-intercept of 0, 2? Does that mean we touched that horizontal asymptote? That means we crossed it, right? Now, I don't know if I crossed from one plane or 1/2 plane to the bottom half plane, but I do know that I interact with that asymptote. So this eventually, and we're running out of time, tomorrow we'll start there and go through the algebra that shows that we do cross the horizontal asymptote. And then we'll take that information and we'll put it on an xy plane and we'll have our rational function graph. And once we can do that maybe 2, 3, 4 times with different questions, then it's the same for the infinite questions that you might ever encounter.